Microchips are ubiquitous in today's technology-driven world, creating increased demand for efficient microchips. They might seem tiny, but their creation is a fascinating process. In this video, we'll explore how microchips are made, and welcome back to How It's Made, folks. Today, we're diving into the world of microchip manufacturing. But before we get started, make sure to hit that subscribe button if you haven't already. So what exactly is a microchip? A microchip is a flat silicon disk with an integrated circuit embedded in it, including transistors. These circuits are formed by embedding materials into the silicon wafer, creating a complex network of tiny switches and interconnected shapes. The construction of these circuits involves intricate processes, which we'll cover in detail. Microsoft, Intel, and Nvidia stand as pillars in the world of microchip manufacturing, each contributing uniquely to the technology landscape. Intel, renowned for its processors, leads to the production of central processing units, or CPUs, and other semiconductor products critical for computing devices. Nvidia specializes in graphics processing units essential for rendering visuals in gaming, AI, and data analytics. Their GPUs are pivotal in accelerating scientific simulations and deep learning tasks. Microsoft, while primarily known for software, also designs custom microchips like the Pluton security processor, aiming to enhance device security in collaboration with Intel and AMD. These companies continually innovate and push the boundaries of microchip technology, ensuring advancements in computing power, efficiency, and specialized applications across industries. Microchips for companies like Microsoft, Intel, and Nvidia are integral to a wide range of practical applications across various industries. Intel's processors power personal computers, servers, and data centers, enabling tasks from everyday computing to complex data analysis and scientific research. Machine learning and autonomous vehicles, where their parallel processing capabilities accelerate computations and enable real-time decision-making. Microsoft's real-time custom microchips, such as Pluton security processor, are designed to enhance the security of devices, safeguarding user data and privacy in PCs, tablets, and other connected devices. Together, these companies drive innovation in microchip tech, enabling advanced capabilities that underpin modern computing, communication, and technological progress globally. Silicon, often referred to as digital gold, is a crucial semiconductor in the tech industry. Manufacturers enhance its properties by adding elements like phosphorus or boron. The great news is that silicon is derived from sand, which is the second most abundant element on Earth after oxygen. Silica sand, a form of silicon dioxide, is the starting material for silicon wafers. The process begins by melting the sand into a large cylindrical shape called an ingot, from which thin wafers are sliced for microchips. High-purity silicon is essential, allowing only one impurity atom per 10 million silicon atoms. Silicon balls are produced in various diameters, with the most common wafer sizes being 150, 200, and 300 millimeters. For microchips, the silicon wafers need to be extremely thin, achieved through a specialized sawing technique. Why is silicon used? Silicon is an efficient semiconductor, capable of conducting electricity under specific conditions. Each silicon atom has 4 outer electrons, making pure monocrystalline silicon non-conducive at room temperature. To make it conductive, small amounts of certain atoms are added as impurities in a process called doping, typically using boron and phosphorus. These elements are near silicon and on the periodic table, sharing similar properties. And the p-type and n-type conducive layers are crucial, with transistors built on these layers. Transistors are the smallest control units in microchips, managing electrical voltages and currents, and are the most critical components of electronic circuits. Each transistor on a chip includes p-type and n-type layers made of silicon crystals, with an additional silicon dioxide layer acting as an insulator topped with a layer of conducive polysilicon. How are microchips made? Step 1. Layout and design. Microchips are meticulously designed due to their complexity, comprising billions of integrated and interconnected transistors forming intricate circuits like microcontrollers and cryptochips. The design process involves measuring and outlining a few square millimeters with a detailed plan defining the chip's function and determine its capabilities and technical and physical properties. This in-depth design process is crucial to characterize the chip's capabilities. In fact, specialized design tools are used to create plans for integrated circuits, constructing a three-dimensional architecture or layered structure. These blueprints are then transferred onto photomasks to introduce precise geometric images of the circuits. During chip fabrication, these photos masks serve as a template to ensure the microscopic structures on the microchip are accurately replicated. These patterns must be created in a dust-free environment with stable temperature and humidity. Microchips are manufactured in clean rooms where strict standards ensure no more than one particle of dust larger than 0.5 micrometers is present in approximately 10 liters of air. These facilities are highly sophisticated, circulating several million cubic meters of air per hour with hundreds of air regulators maintaining constant airflow. Employees adhere to stringent dress codes. Chips are assembled on silicon wafers cut from ingots with several dozen to several thousand chips produced on a single wafer due to their small size. The wafer's surface is oxidized at around 1000 degrees Celsius to create a non-conductive layer, following a uniform application of photoresist material and centrifugal force to create a light-sensitive layer. The wafer is exposed to light through steppers, transferring complex circuit designs onto the silicon. Developed areas reveal the oxide layer, which protects unexposed areas. Next, plasma etching removes the exposed oxide, enabling precise microscopic layers to be etched away where previously developed. After cleaning off residual photoresist, the wafer undergoes further oxidation. Polysilicon is deposited on this thin insulation layer, followed by another round of photoresist application, exposure, and stripping to etch off the polysilicon and thin oxide layers. Impurity atoms are introduced onto exposed silicon through ion implantation, altering its conductivity by fractions of a micrometer. After removing residual photoresist, another oxide layer is applied, and the wafer undergoes another cycle of photoresist application, exposure, and stripping. Etching creates contact holes for integration conductive layers, allowing contacts and interconnections to be added using various metal alloys in specialized machines, enhancing microchip efficiency. Step 4. Finishing touches. Photoresist masks are applied to protect unexposed areas during the etching process, ensuring smooth contact with underlying layers and providing a polished insulation layer. A chemical-mechanical polish process precisely removes excess material with micrometer accuracy. These steps may be repeated multiple times in the fabrication process until the integrated circuit is completed. Depending on the chip size and type, the wafer can yield several dozens or thousands of individual chips. Chips are not aligned flush on the wafer due to splintering during sawing, leaving a scribe line between them. This line contains structures used for initial measurements post-production, which are later removed during the sawing process. Chip sizes typically range from 1 square millimeter to a few square centimeters. Step 5. Assembly. Assembly involves placing individual chips into packages and connection terminals, creating thinner semiconductor devices mountable on circuit boards. Various terminal types facilitate numerous connections, and there are also larger ready-made semiconductor components used in power-related applications like trains, electric cars, solar panels, and wind turbines. These semiconductors handle currents up to several thousand amps and voltages in the thousands, necessitating integrated cooling solutions within the packages. Quality checks are crucial, often employing scanning electron microscopes to inspect chips throughout production. Today's microelectronics are incredibly small, comparable to a human hair's breadth, requiring highly specialized and precise manufacturing processes. That was all from us today for this video, folks. For more similar content, make sure to subscribe to the channel. See you in the next one.